Hello, my name is Kevin Heng. I would like to talk to you about the atmospheres of exoplanets and how these are interesting windows into, in fact, probably one of our few windows into the formation history and habitability conditions of exoplanets, uh, and in a chemical sense as well. So I would like to motivate this talk by asking the question first, why are the atmospheres of exoplanets interesting? And I will start by saying that the most basic properties of an exoplanet is mass and radius. So you typically measure the mass using radial velocity measurements, and you typically measure the radius when the exoplanet transits the star, and you can measure how much light it blocks, and therefore infer the radius of the exoplanet, the transit radius at least. But in order to understand these exoplanets more, you want to say a lot more. You want to know the chemical inventory of these exoplanets and their atmospheres. And in order to do this, you would have to measure spectra of exoplanet atmospheres, meaning not just the light from these atmospheres, but how the light splits into different colors and wavelengths. And interpreting these spectra would then yield constraints on the atmospheric chemistry. So how much water, how much methane, how much CO2, and so on. It would hopefully tell you something about formation history. And the ultimate goal for some astrophysicists at least is to measure the atmospheric chemistry and make statements about how habitable the exoplanet is. And in fact, one of the prizes that we really want to claim in the study of exoplanets is to hunt and detect extraterrestrial life. And I would claim that short of mastering interstellar travel, which doesn't seem to be a realistic goal in the near future, um, the the alternative path is to detect biosignatures gases from spectra of exoplanetary atmospheres. And as I will try to give you one or two examples in the talk, whether a gas is a robust biosignature depends rather strongly on the atmosphere it's embedded in. So uh, this is every exoplanet scientist's dream. Is a it's a dreamscape where you look up and you see companion planets and the star in the sky. In this cartoon, this is an artist's description of what one of the TRAPPIST-1 planets would look like. And the dream is that one would land some kind of rover, similar to in this picture. This is a cartoon of the rover landing on Mars, and that this rover would take samples and photographs and send it back to us, and we would know a lot about the planet. Unfortunately, reality is a bit less spectacular than this. The reality is that for all of these exoplanets, um, we see point sources of light in the sky, and we have very little chance at the moment to travel to one of these exoplanets. And therefore, the next best thing that one can do is to take the light from the planet, split it into different wavelengths, a spectrum, measure a spectrum, and analyze this spectrum for chemical signatures. So in this plot, what you see is the actual atmosphere of the Earth obtained using light that has been reflected from the moon. It's a very interesting study by Enric Paillet et al. In 2009. I encourage you to read this paper. And the claim is that this spectrum has high enough signal to noise and spectral resolution that you can actually start to see signatures of ozone and oxygen and water and methane and carbon dioxide in the spectrum. And in order to make these kind of claims, you would have to go from the measured spectrum to chemical species and abundances, which means you have to solve the inverse problem. And this inverse problem in exoplanet science is called atmospheric retrieval. And I'll spend a large part of the talk talking about the challenges of atmospheric retrieval. So here's the agenda. I will give you some motivation and background for the subject. I will talk about how spectra can be interpreted using both conventional or classical Bayesian techniques and machine learning. And I'll end with big picture questions for the future. So two of the workhorses techniques in exoplanet science are the radial velocity method and the transit method. The radial velocity method is the idea that the star and the planet orbit a common center of mass, so that as the exoplanet goes around the star actually doesn't stand still, but it wobbles about this center of mass, which is typically inside the star itself, but not exactly at its center. And because one can measure light from the star and one can measure spectral lines from the star, one can actually measure how this wobble by the red shifting and the blue shifting of the light as the star moves back and forth along our line of sight. This is the radial velocity technique. This is the technique that won Didier Queloz and Michel Mayor the Nobel Prize for their discovery of the first exoplanet around a sun-like star. And in recent years, it has been realized that, as I will show you, that you get for free, using this technique, high-resolution spectra of exoplanet atmospheres as well, which contains chemical information about the atmosphere. The other technique, which is the transit method, has been really successful, has been shown to be really successful in recent years with missions like the Kepler mission, the TESS mission, and now the CHAOPS mission, and in the future, the Plato mission. And if one can measure multi-wavelength transits, one can also say something about the chemistry of the atmosphere. And so, as I already mentioned, the hope is that once one can go from the spectra to chemistry, then one can say something about the formation history of the planet if it's a gas giant, because for gas giants, the atmosphere retains some memory of the formation history. And for terrestrial exoplanets or super Earths, these are likely to be secondary atmospheres, meaning that the chemistry of the atmosphere is regulated by biogeochemistry, or at the very least, geochemistry, which largely erases the memory of the formation conditions. And is against this geochemistry that one has to understand if there are biosignatures. So let's review some of the observational state of the art. One of the workhorse instruments on the Hubble Space Telescope that has been used to measure transmission spectra is the so-called Wide Field Camera 3, WFC3 for short in the community. And it took astronomers several years of iteration and hard work to figure out how to reduce and calibrate the data and to trust that the signals that they are getting are not just systematics or artifacts. And the wavelength range of WFC3 is from roughly 1.1 to 1.7 microns. And there's a collection of water lines, a water feature at roughly 1.4 microns. It's a feature because the resolution is not high enough to resolve the individual water lines. So you see all of the millions, if not billions, of water lines being squashed together into a feature. And the idea is that if you measure the transit depth or the size of the exoplanet or the shadow that the exoplanet casts on the star, when you measure it, and if the planet has water in its atmosphere, if you measure the size of the planet at roughly 1.4 microns, this planet is going to look slightly bigger because it's more at this wavelength, the atmosphere, the water in the atmosphere absorbs more radiation. And now if you look at wavelengths that are, say, shorter or longer, say 1.2 microns, the size is going to be slightly smaller. And it's this differential technique of measuring the variations in the projected size of the planet across wavelength that actually encodes information about chemical information about the atmosphere, in this case, water. And this effect is very small, as you can see in the plot. So it took really several years for this technique to be honed and perfected. And there are still lessons to be learned. And to date, more than 40 transmission spectra of WIFC3 have been measured, mostly of hot Jupiters. But what's exciting is that astronomers are starting to figure out how to make these measurements for Neptune-sized exoplanets, and very soon for planets that are slightly larger than the size of Earth. And as the technology advances, especially with the James Webb Space Telescope, this technique will be extended down to Earth-sized exoplanets, we hope. So for the WIFC3 transmission spectra, we now know that the spectral feature probes mostly water. There are secondary contributions from ammonia and methane, and this is debated. And as I already mentioned, the spectral resolution, the wavelength coverage will improve dramatically with the James Webb Space Telescope. The other very exciting development in the history of our literature are so-called phase curves from the Spitzer Space Telescope. And there's this iconic study from Hedda Knudsen in 2007, where she measured the phases of a famous hot Jupiter called HD 189733b, which you see on the left. And you can think of it as like the planet showing almost like the phases of the moon, just like the moon would show its different phases to you. And as the planet goes about its orbit, and you see different phases of it, the flux from the planet is going to get modulated. And if your instrument and your understanding of the instrument systematics is good enough, you can measure this modulation, which is what Hedda Knudsen did. And you can see in the left plot that this spectacular sinusoidal modulation. And you can also marvel at how small these numbers are, especially the secondary eclipse. The secondary eclipse, the primary transit is the planet blocking the light of the star. And what's amazing is that the secondary eclipse is the star blocking the light of the planet. So it's a very small effect, and it took a long time to get to this point. On the right is the other iconic hot Jupiter, HD 209458b by Robert Zellum, which came 7 years after the iconic observation of Knudsen in 2007. And ever since these two groundbreaking discoveries, and there have been others too, astronomers have also used the WIFC3 on the Hubble to measure multi-wavelength phase curves. So now not only do you get 1D information along the longitude of the planet, you also get information in wavelength, which traces different depths of the atmosphere as well. The other development that is really important is, as I mentioned in the beginning, that high-resolution spectroscopy from the ground, which is traditionally associated with radial velocity measurements, can also be used to detect chemical signatures in exoplanet atmospheres. So the key idea is that one takes the cross-section of an atom or molecule, which is only based on quantum mechanics, so it's fairly model independent. And one takes this cross-section and then checks this against the rather noisy data. So you can see two realizations of data. The top panel, these are all simulations. The top panel is good data, and the bottom panel is noisier data, which is typical of what you see in reality. And the orange template is the cross-section of the atom or molecule. Now, the data is noisy enough that it's really hard to look at just one specific location of the data and infer anything meaningful. But the idea is that the cross-section contains dozens, if not hundreds, of spectral lines. And by checking the positions of these dozens, if not hundreds, of spectral lines, and also their relative positions against relative to each other, one can actually infer if this molecule or atom is actually present in the exoplanet atmosphere. And this technique was first demonstrated by Ignaz Snellen at Leiden University in 2010. And ever since then, there has been a really string of really exciting results from Ignaz and his team, including from one of Ignaz's ex-students, Matteo Broggi, who provided these movies. So this is a very powerful technique because it only requires that you trust the cross sections of atoms and molecules to make an identification. It turns out it's much harder. It is relatively easy to say if a molecule is present or not in the atmosphere. And it's much trickier to say how much of the molecule is present at what temperature or pressure. And this is partly because it turns out that when you measure these spectra from the ground, because you have to correct for the influence of the Earth's atmosphere, this correction leads to a loss of empirical normalization in the transmission spectra. In other words, in the transmission spectra, you can measure relative transit depths and not absolute transit depths. And this means that you can measure relative abundances and not absolute abundances. For example, you can say how much water there is relative to, say, methane, but you couldn't say, infer the absolute abundance of water. So another example of this technique comes from Jens Humakers, who used to be a postdoc in my research group and was a student of Ignaz Snellen. And I'm showing you this analysis because this was a really convincing example of a detection, in this case of iron in the atmosphere of an exoplanet called Kelt 9b. And in the very top panel, what you see is on the horizontal axis is the red or blue shift. And this is the red or blue shift of the planet as it orbits its star. And on the vertical axis is the time. So as the planet goes around the star, one sees a red and blue shift of a collection of iron lines relative to the star. And now, if you sum up this streak across blue or red shift, you get a clear detection of the iron line in the middle panel. And now, if you fit a Gaussian relative to the background noise of this detection, you end up with a very high number of sigmas of detection. So this is a very robust detection. There's no doubt that iron is there, but like I said, it's much harder to figure out how much iron. So I hope this gives you a sense of the state of the art of the observations of exoplanet atmospheres. I'm a theoretician by training, and my work is predominantly in theory with some implications for data analysis. So this is really a theoretician summary of observations, and I encourage you to listen to actual observers for the details of the observations. So as a theoretician, I often ask the question, how does one make impact? It is clear that one can be really successful as an observer, especially in this exciting era with different space telescopes and ground-based telescopes as well. One can certainly be very successful using the Hubble Space Telescope and soon the James Webb Space Telescope and the ARIEL mission as well in the coming decade. And one can be also very successful mastering high-resolution spectroscopy from the ground, especially with this whole fleet of next-generation spectrographs. But one can also be successful being a theoretician who cares about not just the theoretical foundations of the study of exoplanet atmospheres, but also about how to apply these theoretical foundations into state-of-the-art data interpretation techniques. And these are the two areas that my research group focuses on. And we spend a fair amount of time working closely with observers to learn their language and ideas. So in the next part of the talk, I would like to talk to you about some of these ideas. I would like to focus on transmission spectra rather than emission spectra. And I would like to first focus on the use of traditional Bayesian methods of interpretation. So this is called atmospheric retrieval, as I have mentioned in the beginning of the talk. And the idea is to interpret the data, in this case, a transmission spectrum, and infer chemical abundances from the spectra. So you start with the data. In our case, you need something called a forward model. The forward model would convert opacities, which are cross-sections per unit mass, and assumptions about chemistry. So you need some kind of chemistry model that tells you the relative abundances of atoms and molecules. And you need a forward model to convert these opacities and chemistry into a synthetic spectrum. You would like to pay close attention to your prior beliefs, meaning the prior distributions of the parameters. So for example, a reasonable prior belief is that certain quantities can only be positive and not negative. And you probably have some prior beliefs about what is the maximum or minimum temperature in an atmosphere. So you put these into your forward model, and you explore the multi-parameter space using a sampler and optimizer. Standard techniques include Markov chain Monte Carlo or nested sampling and so forth. And these samplers will give you the posterior distribution of parameters, which in our case are the chemical abundances, how much water, how much methane, the properties of the temperature profile, cloud properties, and so on. And for some techniques, such as nested sampling, one can also formally enforce Occam's razor, meaning one can ask the question, what is the simplest model, excuse me, that provides an adequate explanation of the data? And more complicated models are penalized given the quality of the data. This is called model selection, and I'll walk you through this in the coming slides. There's one golden rule that I always tell my students and postdocs, which is when you do theory or modeling, which is garbage in, garbage out. So if you put in garbage, you're going to get out garbage. Another way of saying this is that fancy statistical or machine learning techniques are no substitute for a sound understanding of physics and chemistry. You need both to do sound research, and you cannot rely on black box techniques to build out your weak understanding of physics or chemistry. So one of the things that we worried about along these lines was something called the normalization degeneracy, which I'll describe to you. This is summarized very nicely in a visual way by a 2014 paper by Caitlin Griffith. And this was also noticed numerically by Benneker and Seeger in 2012. And in this plot, what you see is some Hubble WIFC3 transmission spectra. It's not important which object. And the error bars only show to give you are only there to give you a sense of how uncertain the data is relative to the model predictions. And overlaid on this data are 4 theoretical models. And it turns out that there's a freedom to specify the normalization of these models, meaning you can shift these transmission spectra up and down with no loss of generality. And so here, the author plotted 4 choices of so-called reference radius. So in these models, you need to specify a certain reference radius. And the author intentionally changed this reference radius by only a tiny amount in the second decimal place, as you can see. And astonishingly, this variation of the reference radius in the second decimal place leads to a variation of the water abundance by 5 orders of magnitude. And you can see that the differences between the 4 models are so small that they are essentially undetectable. They're much smaller than the typical error bar on these data points. So these 2 studies did a really good job of pointing out this normalization degeneracy. They didn't call it this. This is my terminology for it because it describes it well. But they did not provide a theoretical explanation for it. So in the following, I'm going to provide you a theoretical explanation. So it turns out that if you accept certain assumptions, meaning that if you accept that the line of sight that defines the transit radius, colored in yellow in this cartoon, if you assume that this line of sight is isothermal, meaning it has the same temperature, and you assume that is isobaric, meaning that it probes roughly the same pressures, then you can actually derive a closed form solution for the transit radius. And this is the outcome of a long string of papers going back to the classic paper by Le Chevalier et al. In 2008, DeWitt and Seeger, Bertrand and Swain, and Jordan and Espinosa, and so on. And our contribution to this was a paper in 2017 by Heng and Kitzman. And what we pointed out was that, look, as others have noted, you can write the transit radius as a reference radius, R0, plus something called the pressure scale height, which is kT over mg. K is the Boltzmann constant, T is temperature, m is the mean molecular mass, and g is gravity. And the pressure scale height is the characteristic height in the atmosphere that is in hydrostatic equilibrium. And the pressure scale height is multiplied in square brackets by a bunch of stuff. There's a factor of a few. And what is really crucial are not these various quantities that I have labeled, but are these three quantities. So it turns out that one needs to specify what reference pressure corresponds to this reference radius. And this is impossible to do from first principles for a given planet, because it requires that one knows the structure of the planet exactly. And one doesn't know this from the transmission spectrum. To compound matters, it turns out that lying right next to the reference pressure in this formula is the opacity. And the opacity is constructed from not just the individual opacities or cross-sections of the individual atoms and molecules, but it's also weighted by their individual abundances. So what is of interest to us are these individual abundances, like the abundances of water and so on. But unfortunately, the opacity is multiplied by the reference pressure, meaning that if you increase the reference pressure, you can compensate by decreasing the opacity or the abundance. So there's a degeneracy. And even worse, since these two quantities are hidden in the log, it means that a tiny change in the reference radius needs to be compensated by an enormous change in either the reference pressure or the opacity. And this is the origin behind the normalization degeneracy that was noticed in 2012 and 2014 by the two sets of authors that I mentioned. So the correct thing to do then is to fix one of these quantities, say the reference radius, and include the reference pressure as one of the fitting parameters in the fit. So here's one example of the WIFC3 transmission spectrum of HD 189733b, which is a hot Jupiter. And on the left, what you see is the model that best fits the data, or I will explain what that means in a minute. And this model is relatively simple. It assumes one temperature, it's an isothermal transit chord through the atmosphere. It assumes just the presence of water. It assumes that there's a cloud, but that the cloud has particles that are much larger than the wavelengths being probed, meaning that the cloud can be described by just a single number, which is because the cross-section is constant. And finally, you also have to fit for the reference pressure, as I mentioned earlier. And it turns out that, for example, if you focus on the water abundance, the posterior of the water abundance, meaning the probability distribution of the water abundance, is bounded on both sides. It falls off on the side towards high water abundances because of physics. As you increase the water abundance in an atmosphere, the mean molecular mass of the atmosphere increases, meaning it gets more metal rich, so to speak. When it gets more metal-rich or water-rich, the pressure scale heights becomes smaller, but the measured feature that you see stays the same size. So as the theoretical scale height becomes smaller, it means that one needs more and more scale heights to describe the same size of feature. And now if you keep increasing the water abundance, soon you actually run out of scale heights to describe the feature, which is why the posterior starts to drop off towards the right. The drop off on the left turns out to be not real in the following sense. Because we do not really know what the physical range of values of the reference pressure actually is, we had to impose some kind of prior belief. And the prior distribution we impose is that the reference pressure has a maximum value of 1,000 bars, so 10 to the 3 in that plot. And it turns out that the posterior of the reference pressure bumps up against the prior, so it's prior dominated. And this right side of the posterior of P0 corresponds to the left side of the water abundance posterior. So the left side of the water abundance posterior is actually prior dominated. If you want to know more about this issue, you can either talk to me in the Q&A, or you can look at the backup slides in this same lecture, and this will give you more information. Now I would like to talk more about Bayesian model selection. So in this study that one of my PhD students, Chloe Fisher, did, she didn't just fit it with the model that we just spent a lot of time talking about. She fitted it, the data, the transmission spectrum, with a whole family of models. So if I read the models from left to right, there's the model that's isothermal with gray clouds and water only. And then the second model is a non-gray cloud, meaning the cross-section is not constant, but water only and isothermal. The third model has a gray cloud, but in addition to water, has ammonia and hydrogen cyanide and so on. You get the idea. So there's a whole different family of models with different levels of sophistication. And for each model, one can calculate something called the Bayesian evidence. And now, if you take the ratio of the Bayesian evidences and you take the log, this is called the Bayes factor. And the Bayes factor is always a comparison between a pair of models. And now, if you line up the models from highest Bayesian evidence to lowest Bayesian evidence, you can then take the Bayes factor relative to the best model, which is what you see in this plot. So it turns out that the model of the highest Bayesian evidence is the model with gray clouds, one temperature, and water only. And all of the other Bayes factors are labeled in the plot, as you see. And it also turns out that there's a rather established literature on how to interpret these Bayes factors. So models that have Bayes factors less than 1 relative to the best model, the one of the highest Bayesian evidence, can all explain the data. So in other words, all of the models that you see on this plot in green are acceptable explanations for the data. Models with Bayes factors relative to the best model, that are between 1 and 2.4 are weakly ruled out by the data. These are the models in blue. And models with Bayes factors up to 4.9 are moderately ruled out by the data. In the case of this data set, this would be the flat line. So the Bayes factor says that a flat line is not a good explanation for the transmission spectrum of HD 189. So Chloe repeated this type of analysis for 38 objects at that time anyway. In 2018, there were 38 with C3 transmission spectra. There are now more. She then excluded the objects where the transmission spectra are consistent with flat lines. And then she plotted the inferred water abundances versus the mass of the exoplanet on this plot that you see. And she shaded the data points, the entries, darker or lighter according to the gravity of the planet. And you can see that it looks largely like a scatter plot. There's not a convincing indication of a correlation between the water abundance and the mass, or at least if there's any correlation that is tentative. And this is an aspiration of the exoplanet atmospheres community. Our hope is that not only will the data get good enough with James Webb, but we will understand these issues like the normalization degeneracy and atmospheric chemistry well enough that we can drastically reduce the uncertainties on these inferred water abundances, and that when one plots these against some property of the exoplanet or the star, there will be trends that tell us something about the formation history of these exoplanets. Um, this remains an aspiration for, I would claim, for Hubble data, but this field is going to grow by leaps and bounds in the era of the James Webb Space Telescope. At least I'm very hopeful. So this was the use of the traditional Bayesian approach to perform atmospheric retrieval. And at the same time, I was thinking about how may we go beyond the traditional Bayesian approach. And there were several reasons why I was thinking these thoughts. One of them was because of feasibility. So when one actually runs a atmospheric retrieval with, say, a nested sampling or MCMC approach, typically one has to design a forward model that's fast enough that you can calculate the forward models on the fly. And since you have to run the MCMC for hundreds of thousands of steps or even more, ideally each forward model should be evaluated in a fraction of a second. And in order to make the model this fast, one inevitably has to make compromises to the physical and the chemical realism of the forward model. And so there's always a tension between computational feasibility and physical realism. And I was wondering how one could actually decouple these so that one could make models that were as realistic as one wanted them to be, and yet have the retrieval complete in a reasonable amount of time. And eventually this chain of reasoning led me to machine learning, because it turns out that certain classes of machine learning methods are capable of doing Bayesian inference, or at least approximate Bayesian inference. And one can always use grids of models as training sets for these machine learning methods, which effectively decouples the model building part from the inference part in two separate logistical steps. So let me talk about some of these ideas, and hopefully they will inspire you to make things even better. So to talk about this, we have to go back and talk about Bayes' theorem. What is Bayes' theorem? Mathematically, Bayes' theorem was a mathematical relationship written down more than a century ago by Reverend Thomas Bayes. It's a relationship between the posterior of a parameter of a model. So it's the probability distribution, in our case, of atomic or molecular abundances, the temperature, cloud properties, and so on. And this is a function of our prior beliefs on these parameters, multiplied by something called the likelihood, which I will describe in a moment, and divided by the Bayesian evidence, which we just spent a lot of time discussing. The likelihood, if you think about it, is the relationship between the data, the model, and the noise. It is not a probability, but a relationship that allows you to then scan parameter space to find the optimal fit between the model and the data, given the noise. And a common assumption made in the atmospheric retrieval literature is that this likelihood is Gaussian. And so one of the things that I worried about was whether this assumption is robust, and how do we move beyond this assumption. And it turns out that there's a part of the literature that thinks the same thoughts, and this is called approximate Bayesian computation. This is a branch of applied statistics that was invented by epidemiologists studying trends in human populations. And the reason why they were forced to go this route was because when one studies anything to do with biology, one cannot write down equations from first principles. So writing down the equation itself to describe the system is already difficult to begin with, and the likelihood of the system is either impossible to write down or very difficult to compute. And so approximate Bayesian computation is a way to do Bayesian inference approximately without having to write down the likelihood explicitly as a function. And this has often been described as likelihood free because one doesn't need to write down the likelihood, but this is a misnomer in the sense that it's not that the likelihood is missing from the system, because the mathematical relationship between the data, the model, and the noise is still there. It's just that one doesn't need to write it down to perform this inference. And the likelihood may be expressed not just through the writing down of equations. It can be expressed through simulations, and it can also be expressed empirically through data. And the fundamental difference from standard Bayesian methods, as far as I can tell, is that instead of maximizing the likelihood, one minimizes some abstract distance, like a Euclidean distance, between the data and a set of models, subjected to some tolerance between of the difference between the data and the model. So one of the methods that really caught our attention is the method of the random forest, which happens to be an ABC method. And I'll start by describing the random forest by describing an individual decision tree. And it's not really intimidating if you just visualize it. And so this is a decision tree where we are trying to classify fruit. So we have a banana, apple, and a lemon. And we classify fruit by asking questions. So we ask questions like, is the fruit sweet? And this separates the banana and the apple from the lemon. I'm assuming a sweet apple. And then you can ask questions like, is the fruit roughly spherical? And this would then separate the apple from the banana. And now your question, and this would train the decision tree to classify yellow bananas, apples, and lemon, such that now if you ask the decision tree to classify a green unripened banana, it would have no answer for you. So this is again a key aspect of machine learning, which is that you are only as good as your training set. And it turns out that where the tree terminates, which are called leaves, are basically approximate samplings of the posterior distribution of parameters. In the case of decision trees, where objects are discrete, these parameters are called labels. And so the leaves are sampling the posterior distribution of these labels. So you must be wondering, what has classifying fruit have anything to do with classifying spectra? So when one deals with continuous properties like fluxes instead of discrete objects like fruit, one deals with regression trees. And even though this seems very different, conceptually it's very similar. So instead of asking questions about sweetness or roundness, you now ask questions like, is the ith data point higher than some threshold d sub I? So this allows you to then split the training set of spectra into spectra that are more similar or different from one another. You then ask another question, which is the jth data point. Is the jth data point higher than some threshold d sub j? And you choose these thresholds and you randomize on asking which data points in such a way that the information entropy of the entire regression tree is minimized. So if you are interested in a description of this, there are two references that I recommend you read. The first reference is a very long report/paper by Criminisi et al. In 2011, which describes the use of regression trees as approximate posterior samplers. And also the textbook that I just flashed to you in the previous slide by Sesson et al., which describes random forests, which are collections of regression trees as a class of ABC method. So in 2018, we put together a paper describing the application of this well-known method to atmospheric retrieval. And the idea is to train a collection of regression trees on a set of transmission spectral models and combine this with a method called bootstrapping, which ensures that each regression tree in the random forest is constructed in an uncorrelated way so that you can actually use it to sample posterior distributions. And the way to visualize it is to think of each tree in the random forest as like an independent voter. So you show this collection of voters, this collection of trees, the measured spectrum, which are the red data points in the top left, and you ask them questions like, what's the temperature? How much water? How much of other molecules? How cloudy is this atmosphere? And each voter, each tree would return you a set of answers, which you see as a dispersion of entry points in the right plot. And once you aggregate these entries from all of the voters, this would give you an ensemble of points that are essentially a approximate sampling of the posterior distribution. So in the paper, we showed that the random forest produce a atmospheric retrieval outcome that is comparable to the nested sampling method. But this is not primarily the reason why we were interested in the random forest, because we were interested because the random forest not only does the traditional retrieval approximately, but it also gives you other features that are difficult to get using the classical methods. And one of these features is the so-called information content analysis. So in practice, what one does is that one takes a training set of models of transmission spectra, for example, and one uses 80% of the grid of models to train the random forest. Using and one then uses the last 20% as a test on if this training has worked successfully. So in this plot, what you see, for example, is for each point entry on the plot is a so-called mock retrieval. So we are retrieving on a spectrum for which we created, so we know what the correct answer is. And so we compare the real answer of, in this case, the abundance of carbon monoxide with the predicted answer, and we see how well we do. And the reason why this is important is because you can use this to answer a question, which is, how do we optimize our use of James Webb Space Telescope time for studying exoplanet atmospheres? And this is a function of the type of observing mode you choose on the James Webb, which is a function of not just the spectral resolution, but also the range of wavelengths that's being captured by each instrument. So as an example, on the left, there's this instrument called the NearSpec G140M, the medium resolution. And you can see that the range of wavelengths covered is such that it's not very sensitive to the presence of carbon monoxide. So you can see that the predicted versus the real abundance of carbon monoxide doesn't do very well at all. And in fact, there's a number called the coefficient of determination, R², which measures how predictive this process is. And when R² is 1, it means that it's perfectly predictive, and when it's 0, it means there's no predictability. And you can see in this case that the R² value is very close to 0. On the other hand, if one uses a different instrument mode on near spec, which covers roughly 3 to 5 microns, as you see on the right, then this R-square value increases dramatically. The reason why the R-square value is not exactly 1 is because of noise. We have inserted realistic noise in this calculation. And second, because of model degeneracies, meaning that different combinations of parameters can give you roughly the same spectrum. And these degeneracies are present even when you have very ideal data. And these two factors combine to give you to make sure that this real versus predicted cloud of points is not a straight line on the diagonal, but rather a cloud of points. These plots also give you a sense of what's the minimum detected abundance of a molecule given a noise model. So in this example, you can see that the minimum detected abundance is roughly 1 part in 10 million. So this is useful because this allows you to select the range of wavelengths to use for detecting the molecule or atom you want to detect. And the other feature of the random forest, which also goes along this direction, is something called the feature importance analysis. So this tells you, as a function of wavelength, how important each wavelength is in determining the value of a parameter. And so I've shown a collection of examples using this instrument spanning 3 to 5 microns on the James Webb near spec. And you can see that, for example, carbon dioxide, which is the lower right panel, has a cluster of entries near 4.5 microns, which is also one of the channels of the Spitzer Space Telescope. Is consistent with the notion that the Spitzer Space Telescope in its 4.5 microns channel can detect the presence of carbon dioxide. You can see that there are multiple wavelengths that are sensitive to temperature because temperature is determined by the different molecules present, and so on. And so this feature importance allows you to check your intuition about which wavelengths are important for detecting different molecules. And this is work done by one of my PhD students, Andrea Guzman Mesa. And now this is a plot that brings it all together. So on this plot is the coefficient of determination, where 0 means no predictability and 1 means perfect predictability, as I explained to you. And on the horizontal axis are the different parameters of the transmission spectra we've considered in this study. And the different symbols correspond to the different instrument modes on the James Webb near spec, as you see in the table on the right. And you can see that, for example, the blue modes do quite well in general, except for detecting carbon dioxide and carbon monoxide. And the red modes do much better at CO and CO2. And in fact, the mode that we recommended in this study is the mode between 3 to 5 microns, because this is a good compromise between detecting all of the major molecules of interest and also inferring the values of the cloud properties. So this ends the part on using machine learning to do at least retrieval of space-based data. At this point, I would like to talk to you about ground versus space-based spectroscopy. So it is certainly true that if you measure spectra from the ground, in general, the spectral resolution is orders of magnitude higher. The spectral resolution is typically a few 100,000 to even 1 million for the next generation spectrographs. And from space, using the James Webb, one would get a few hundred to a couple of thousand. However, what you give up on the ground is because you have to observe through the Earth's atmosphere, there's a very high level of noise present in the data. And I'll show you in the next slide that this implies that traditional retrieval methods do not actually work. Observing from the ground and dealing with the Earth's atmosphere also means that there's a loss of empirical normalization, with the consequence that one can only measure relative abundances and not absolute abundances. From space, the resolution is lower, but the price that you pay is that the individual spectral lines are unresolved, whereas using ground-based high-resolution spectroscopy, you can actually resolve individual spectral lines. And from space, one doesn't have to deal with the loss of empirical normalization, meaning that one can actually measure absolute transit depths and not relative transit depths. But one has to then deal with the normalization degeneracy, as I described to you. So if you've been paying attention to the talk, then obviously the correct way to go forward is to combine the advantages of two methods and try to leverage them against each other to mitigate the weaknesses of each method. But before I do that, I want to show you something I mentioned, which is the failure of direct retrieval in high-resolution spectra. So this is a simulation of a spectrum. It's not a real spectrum. But the error in this spectrum is empirical. It's measured from a telescope. And this is of an object called Kelt 9b from this paper. But it doesn't matter what object, as this discussion is generic. So if you look at the top right panel, you will see that the simulated data points are in light purple, but the error is in gray. And you can see that for each individual data point, the error is much larger than the central value of the data point itself. And the model is given in dark purple. And you can see again that the features in the model are dwarfed by the size of the noise. So if one runs a traditional retrieval method on this noisy data set, what one is really doing is that one is trying to extract information on a point-by-point basis. And not surprisingly, when one does that, one ends up with basically no answer with the prior distribution of the parameters. So on the top left plot, you can see the posterior distribution of the metallicity. If one uses a random forest, one ends up with basically an answer that spans the whole range of the prior. And when one uses nested sampling, one ends up with the wrong answer. And the real answer is the vertical dashed line. On the bottom right corner is the posterior of the temperature. And again, the random forest gives you back no answer, and the nested sampling gives you an answer that is not coincident with the truth, meaning the answer that we know is being fed to the model. And so the conclusion is that one has to try something else. And in fact, this the failure of interpretation on a point-by-point basis is precisely why astronomers have used the cross-correlation method. The idea behind the cross-correlation method is that while each individual data point is swarmed by noise, one can combine the information from many data points to actually leverage a signal of the data. And a really important paper that combines both cross-correlation with traditional retrieval and combining the two data sets is this paper by Broggi and Line in 2019. So what these authors did was they jointly analyzed a WIFC3 emission spectrum, so shown by the black data points, and also a high resolution spectrum measured from the ground in blue. As you can see, the data is very densely packed. And what they figured out was very clever. They realized that there's a analytical relationship between the cross-correlation function and the likelihood function. And once they figure out this relationship, it means that they could then use the traditional Bayesian methods that are likelihood-based on the high-resolution spectra using cross-correlation. And one can then do a joint analysis of both the low and the high-resolution spectra. And they showed very convincingly in this paper that if you do either analysis by itself, meaning either cross-correlation of the high-resolution spectra or traditional retrieval of the low-resolution spectra, you get a worse answer than if you combine the two, which is shown in pink in these posteriors and temperature pressure profiles. And this was a very convincing demonstration of the combination of the two methods. The challenge here is that because this is fundamentally still a likelihood method, and this was demonstrated on high resolution spectra with only 4,000 data points, it becomes quite challenging to scale this up by 2 or 3 orders of magnitude. And this is because the next generation spectrographs typically have hundreds of thousands, if not millions of data points. So one has to analyze these data a different way because there's 3 orders of magnitude more data. And one way to do this, we claim, is using machine learning. And one needs to talk about something called feature engineering in machine learning. So typically what one does is that one has a training set, like a grid of models, and one feeds this training set to a box, sometimes a black box. And techniques like deep learning would then extract the informative features from this training set, and one ends up with a trained classifier. And the reason why convolutional neural networks and its kin are so powerful is because this feature engineering step is done automatically. The downsides of using deep learning for this is that neural networks are generally very expensive to run. And there's some debate on whether neural networks actually produce posterior distributions in the true Bayesian sense. So we took a different approach. We combine cross-correlation analysis with the random forest. So again, one starts with a training set of models. And we do the feature engineering manually. What we do is we create templates from cross-sections of the atoms or molecules we want to detect. In this case of Cal9, these are iron and titanium. We then cross-correlate these templates with the grid of models. And the big surprise is not that you can actually do this. The big surprise is that you can cross-correlate the templates with the model spectra at very sparsely sampled combinations of the parameter values. And this sparsely sample is the key because this allows a dimensionality reduction of 2 to 3 orders of magnitude. One then ends up with a random forest of trained CCF, cross-correlation function sequences, that one can then use to analyze the data. So here's one example of a CCF sequence. So instead of a training grid of thousands, if not hundreds of thousands of spectra, we reduce that training set to a set of CCFs. And the reason why is these are functions and not numbers is because one has to construct these cross-correlation functions over redshift as well. So if you are interested in the details of this, I encourage you to read Fisher et al. 2020, where the reference is stated below. In this study, Chloe Fisher, one of my students, also tested the random forest against other machine learning methods. So one method that she tested this against is called the Bayesian neural network. And one can debate how Bayesian the Bayesian neural network is. It does pretty well in this example. So in this example, we know what the truth value is for the metallicity in red and the temperature in blue. And the truth value is a dashed vertical line. And you can see that it does pretty well. In other instances, when the posterior distribution is bimodal, as in this case, and we understand physically why it's bimodal, the random forest gives a more conservative answer, and the Bayesian neural network goes a little bit awry, at least on the metallicity. And this area of research continues to be very active, and as the use of machine learning methods for retrieval becomes more and more commonplace, these are the type of things that we should really explore to understand the strengths and weaknesses of each method. So I've spent about 2/3 of the talk talking about interpreting spectra using both classical Bayesian techniques and also machine learning techniques. I would like to end the lecture talking about the big picture questions and the future of studying exoplanet atmospheres. And I would like to focus on 3 topics. I would like to talk about mini-Neptunes and try to convince you why they are so interesting. I would like to talk about geochemical cycles, and would like to talk about biosignatures. So let's start with mini-Neptunes. Why are they interesting? So it turns out that in a sense, the solar system biases our thinking. Because in the solar system, we have 4 gas or ice giants. And these gas or ice giants have so-called primary atmospheres, meaning these atmospheres are made mostly of hydrogen and helium. And they retain a memory of the primordial nebula out of which all of the planets form. And the idea is that if you can study the atmospheric chemistry of the primary atmosphere, you can then extract information about the chemistry and therefore constrain the formation history. We also have terrestrial rocky planets in our solar system. And these have secondary atmospheres, meaning the atmospheres have lost memory of the primordial nebula. They are certainly not hydrogen or helium dominated. And instead, the chemical composition of these secondary atmospheres are determined more by processes like geochemical cycles, magma-atmosphere interactions, and in the case of Earth, biology. For example, the Earth is about 78% nitrogen, about 20% oxygen, and with water and carbon dioxide as trace gases. And the atmosphere of the Earth chemically certainly looks nothing like the sun. Now, it also turns out that because of missions like Kepler and TESS and the ground-based surveys, one of the key findings of exoplanet science is that objects in between gas giants and terrestrial planets are quite common. And they can be objects that are slightly smaller than Neptune or slightly larger than Earth. And we call them mini-Neptunes and super-Earths. I'll describe this terminology in the next slide more. And there's no example of either mini-Neptune or super-Earth in our solar system. And so the natural question to ask is, what are these atmospheres made of? Are these primary atmospheres? Or are these secondary atmospheres? Or more likely, are these some complicated combination of primary and secondary atmospheres? This is really a cutting-edge question with no clear answer yet, partly because we have no example to study in the solar system. The difference between calling them super-Earths versus mini-Neptunes can be traced to an iconic plot that I'm showing you on this slide. And what astronomers have found is that when you plot the size of the planet, the transit radii of the planet, versus the orbital period, and if you understood the properties of the stars very well, you could really reduce the size of the uncertainties on the transit radii. And once one does this, one sees that the planet separates into 2 subpopulations, separated at roughly 1.6, 1.7 Earth radii. And so this separation is commonly called the Fulton Gap. And sitting above the Fulton Gap are the mini-Neptunes, which are thought to have still hydrogen in their atmospheres, or at least the atmospheres are more puffy. And sitting below the Fulton Gap are the so-called super-Earths with thinner atmospheres. And one of the debates that's currently happening in the literature is whether super-Earths are the outcome of objects that were previously like mini-Neptunes and they just lost their atmospheres. And this atmospheric loss has at least two mechanisms that's actively debated in the literature. This is photoevaporation by ultraviolet and X-ray radiation from the star versus core-powered mass loss as a result of the remnant heat of formation. And this debate is still occurring as we speak. And now one really wants to know what's the nature of these mini Neptunes. And as I mentioned, these exoplanets turn out to be really common, and they're discovered in the buckets by Kepler tests and Cheops, the Cheops mission as well. And they typically have radii between 2 and 3 Earth radii. And researchers like Edwin Kite, which is cited in this graph, have pointed out that in this regime of between 2 and 3 Earth radii, the interaction between the magma oceans, the molten rock, early in the life of these exoplanets, and the atmosphere of these exoplanets cannot be neglected. And in fact, for example, the water, the hydrogen from these atmospheres can dissolve in the magma, and this also affects the amount of water in the atmosphere. And so the atmosphere is somewhere in between primary and secondary with no current example in the solar system. And my opinion is that the true value of the James Webb Space Telescope will be to decisively understand the nature of these atmospheres. The second question that I find interesting is, what is the role of geochemical cycles in sculpting the atmospheres of rocky exoplanets? So on Earth, at least, the long-term carbon cycle is responsible for regulating the abundance of carbon dioxide. So volcanoes, both on land and Earth, outgas carbon dioxide and water. Carbon dioxide combines with water and silicate rock to produce weathering. And one of the products of weathering are these carbonates that are then washed in the ocean, are subducted into the mantle, and then outgassed again as carbon dioxide. And this cycle has a characteristic timescale of a couple of 100,000 years. And this cycle is also exerting a negative climate feedback on the Earth's atmosphere in the following sense. So if a lot of carbon dioxide accumulates in the atmosphere, then because carbon dioxide is a greenhouse gas, the atmosphere gets warmer. And it turns out that when the atmosphere gets warmer, the strength of weathering increases exponentially. And this then draws down the carbon dioxide to reduce levels. And this negative feedback also works in the opposite direction. So if the Earth was frozen over and weathering stopped, then carbon dioxide would accumulate till warming occurs sufficiently enough that it breaks us out of this frozen state. So the long-term carbon cycle is a way to regulate the presence of carbon dioxide and therefore the temperature, the surface temperature on Earth. It is unclear how and if these geochemical cycles occur on exoplanets. And the other part of the story that is interesting is that it's important what the chemistry of the gas being outgassed actually is. And if you read papers such as the ones cited on this slide, the claim is that the chemistry of outgassing depends at the very least on quantities like the surface pressure of the atmosphere, which would then determine, for example, if one is like in the regime of Earth, where one outgasses mostly water and carbon dioxide, or if one is in the regime of Venus, where one predominantly outgasses CO2 with not much water, or if one is in the regime of Io, where SO2, sulfur dioxide, is the prominent species being outgassed. And I encourage you to read this really interesting reference on the slide if you want to know more about this. And one of the reasons why we care about geochemical cycles is that this negative climate feedback that I just described to you is an important part of the story of the existence of the habitable zone. So to use Earth as an example, Earth has mostly nitrogen, which is the background gas. Water is the condensable greenhouse gas, and carbon dioxide is the incondensable greenhouse gas. So if you move Earth too close to the sun, then the condensable greenhouse gas, which is water, becomes incondensable. And if you move Earth too far away from the sun, then the incondensable greenhouse gas, which is carbon dioxide, becomes condensable. And these two concepts roughly define the boundaries of the habitable zone. And you can imagine other rocky exoplanets where you have different types of condensable and incondensable greenhouse gases, which then obliges you to know if these greenhouse gases are involved in some kind of geochemical cycle which regulates their long-term behavior. And this is the reason why geochemical cycles are important. And in a recent study done by one of my postdocs, who is partially trained as a geologist, we also found out that, unsurprisingly, the lithology or the rock composition is really important for understanding if the carbon cycle actually exerts a negative climate feedback. We actually found that in some cases, that at least formally, it's possible to have positive climate feedbacks as well. If you're interested in this issue, I encourage you to read this paper cited on this slide. And finally, I would like to speak briefly about biosignatures. There's a very deep literature on biosignatures. One of my favorite set of papers is written by Sarah Seeger, who is a pioneer in exoplanet astrobiology. And there are different ways of thinking about biosignatures. And Seeger's way of thinking about it is distinctly non-Earth-centric. She thinks of all of the small molecules that can be created that obey the laws of chemistry as we know them. She then puts them through different filters. She asks if they are stable or volatile, if they have a geochemical or geophysical false positive, if they are detectable over plausible biomass, and if they are so-called type 1, 2, or 3 biosignatures. Type 1 biosignatures are associated with metabolism, but which means they can be common gases like methane. But type 1 biosignatures also have strong geological false positives, meaning that just because you see methane doesn't automatically mean it's life. It could be also produced by rocks. Type 2 biosignatures are associated with building biomass, and so far no type 2 biosignatures have been identified by the Seeger group at least. And type 3 biosignatures are associated not with metabolism but with physiology, meaning they are not associated with eating and breathing but with functions. And the claim is that type 3 biosignatures, though they are present in very small trace amounts, they have no obvious geological false positives. So here's a example of a type 3 biosignature. This is dimethyl sulfide with the chemical stoichiometry as you see on the slide. And in this paper by Seeger et al. In 2013, they demonstrated that there are scenarios under which dimethyl sulfide might be detectable in the hydrogen-dominated atmosphere of a super Earth. But generally, the point is that there's no magic bullet of a biosignature. There's no magic molecule that one can detect in all circumstances and declare that one has detected biology. It very much depends on the background atmosphere. And here are a list of 5 properties that one should think about when considering biosignatures. Number 1 is that they should be long-lived against destructive processes like photolysis. Whatever is a biosignature gas should be able to accumulate and be replenished in the atmosphere. They should be realistic chances of detection using a telescope. One should be able to distinguish the spectral signatures from other large signals due to molecules that have nothing to do with life. And they should be robust against geological false positives. So as a fun toy example, I take the example from the Seeger et al. 2013 paper, where they reasoned that a process that's very well known on Earth, which is the Hubble process, could be a way of thinking about biosignatures. And on Earth, the Hubble process is the combination of hydrogen and nitrogen to produce ammonia. And this has normally nothing to do with life, but Seeger et al. Imagine a hydrogen-rich world where life finds a way to catalyze this exothermic process and extract energy from it. And so here the biosignature would be ammonia, unless it's destroyed by UV photolysis. And so there are several possible false positives. This process could go by itself if the atmosphere is reasonably hot, so 800 to 1,000 degrees Kelvin. It doesn't need life. This process could also go if the atmosphere is very thick, meaning the surface pressure is very high. There's a possibility that ammonia could be outgassed and not produced biologically. And if the UV photolysis is sufficiently weak, that means that ammonia that was primordial ammonia that was accumulated abiotically would not be destroyed and would be mistaken as biologically created ammonia. So it's tricky. So if you have too much UV radiation, then you destroy all of the ammonia. If you have too little, then you do not destroy the ammonia that has been, the ancient ammonia that has nothing to do with life. And on top of all of this is the question, is there any kind of a weathering cycle associated with ammonia? So this is a fun example of a so-called co-Hubble world. And it makes one think about all these different factors and how to move forward. So to summarize this thinking, to detect biosignatures requires some kind of spectrum, at least on an exoplanet. This requires a state-of-the-art telescope, either in space or from the ground. This requires that you master all of the interpretation techniques that I spent most of the talk talking about. And even after you measure the spectrum and infer the chemical abundances, you have to worry about how to interpret these chemical signatures. You have to worry about whether the signatures that you're seeing are really due to biochemistry, so whether they're true biosignatures, or if you might be looking at false positives generated by geochemistry. There are several upcoming space missions that would make this search for biosignatures even more exciting. So, for example, in 2021, we expect the launch of the James Webb Space Telescope. I think that at this point, the community is not expecting that the James Webb will detect biosignatures in Earth-like exoplanets. But at least the James Webb will make huge leaps in how we measure and interpret transmission and emission spectra. In roughly 2028, the ARIEL mission of ESA will launch as well, although this is focused on studying mostly warm and hot exoplanets. And in the 2040s, NASA is currently studying 4 mission concepts. And it's interesting that 3 of these 4 mission concepts are focused on habitable worlds, so LUVOIR, HabEx, and OST. It's not clear which of these missions will be approved for further study. This remains to be seen. And from 2025 onwards, the extremely large telescopes, both from Europe and the US, will see first light. So exciting times are still to come as the technology keeps getting pushed to greater and greater limits. And I would like to leave you now with an aspirational slide. This is an actual photograph that's taken by the Voyager mission. on its way out of the solar system and turning back to take a photograph of the Earth. And this inspirational photograph coined the term the pale blue dot because that's what we look like from very far away. And you will see that your eyes don't tell you very much about the pale blue dot. You certainly do not see the blue oceans and the white clouds and the continents of different colors. But if you took the light from the pale blue dot and you split it into a spectrum, you will see that this spectrum tells you about the water and oxygen and methane and carbon dioxide that are present on Earth. And if you analyze the relative abundances of these molecules, you will find that they are out of chemical equilibrium, which strongly suggests that life, us, is present. And this is an aspiration that we are aiming for as the exoplanet community. So to end, I would like to say that exoplanet science is in an age of revolution. The study of exoplanet atmospheres goes beyond mere measurements of mass and radius, and is the next logical step in the evolution of this field. The study of the spectra of exoplanet atmospheres yields constraints on atmospheric chemistry, formation history, and we hope eventually habitability conditions. Establishing the theoretical foundations and cutting-edge interpretational methods are key components towards advancing understanding. Making progress requires an interdisciplinary approach that marries astrophysics and astronomy with Bayesian inference techniques, machine learning, geochemistry, and so forth. And my personal opinion is that the next frontiers are the understanding of mini Neptunes and super Earths, not just astrophysically, but also chemically. The understanding of how geochemical cycles possibly operate on other rocky exoplanets, and understanding better what biosignatures are and what their false positives are. And with that, I thank you for your attention over this 90 intense minutes. And I'm happy to answer your questions both in the Q&A and if you write to me in email. Thank you very much.